Basically almost now.
Yeah.
Come on now!
You want
Yes,
Peter? You want Nicola to introduce
Okay, I will. So, but I'm chairing, so I'll ask Nicola to introduce Chang'e.
Yeah, okay.
Yeah, thanks.
So,
it was Roger, but I asked him to get, but I didn't know what. Some, I guess it alternative.
Yeah. Okay, can we start?
Nicola, can we start? You're going to do the introduction, I'm chairing, right? So, well, no nonsense. Okay, welcome to the Thursday of our meeting, ladies and gentlemen. We're going to start with Manian, who is a fellow of the Royal Astronomical Society, and Nicola is going to introduce.
Generally speaking, when I introduce people to Chad, I describe him as an astrophysicist, shaman, business guru. And if you want to hear some interesting stories, you can ask about him, about why I call him a shaman. But he's got a lot of, the whole astrophysics background, but also in terms of just starting things and initiatives in terms of bringing different people together from different academic groups and trying to get fruitful conversations going. This is something that he's been doing a lot, which is really, really great. So, and I just wish he and Mike and Colour could have been in the same place at the same time, because I think
That was my intention, but unfortunately...
No, it couldn't work out, could it? But I told Mike about Chad, and I told Chad about Mike, and they're going to send each other things, so it'll happen.
Thank you and good morning everybody. So to kick off, so this is my talk today, the challenges towards space colonization. So the key issue, central problem that we're dealing with is essentially exploring, getting out there into deep space. Now, this is an up-and-coming topic, and also it's been an area of a lot of debate, a lot of field research, a lot of debate. It's the source of a great deal of discussion currently, and it is at the moment what appears to be a hot topic. But I also consider this to be one of the most significant problems of the 21st century. To give you a little bit of background of where we are, where we got to this, I'm going to go back to the very basics of how this whole situation came about and how we got into this discussion topic. Now, I was asked earlier on this year to do a talk at the science fiction convention, and this was about the challenges towards meeting extraterrestrial life. And for example, you have a lot of science fiction, sci-fi authors and writers, and you have a lot of kids who are now getting involved in STEM and science, and we talk about what about the possibilities of alien life. Would we ever encounter it in the distant future? So I was basically supposed to do it. And I thought about this and I said, you know what? My undergraduate dissertation in astronomy was about the challenges towards finding alien life forms. And a year ago, a PhD student at Birkbeck, the astro team, she was a researcher doing a PhD on astrobiology, which was essentially, her doctorate was about the analysis of the soil sample in Mars. And when they had initially found the Chlorobolus, the very primordial, it's one of the essential, well, not ingredients, but one of the precursors to what you would define as something that leads up to a life form. So it's a very early organic form of matter, organic cells. So they did find something, and of course her research was all about spending a lot of time studying and defining. So is this essentially life or not? So this has been the biggest topic. So what do you classify as life? Now again, going back, finding life is one thing. what is that life? Is it intelligent life? Is it sentient? So you get into a very vast discussion. But before you even go that far, before you can go out there into the surface of the Moon and Mars to excavate, you first have to master the biggest challenge, first building block, getting out there into space. So therefore, this topic, terraforming versus habitation, space colonization or exploration. Now, to give you a little background, there's a timeline of space exploration. The first ever mission that we know of was the Russian Sputnik that was launched in the 50s, 1957, when Russia won the space race, essentially. Yuri Gagarin becomes the very first man in space, first human in 1961, which was still the Soviet Union back at the time. And of course, right through the 60s, Apollo was America's attempt at landing on the moon. It wasn't until '77 when we actually came up with something a bit more sensible towards exploration, launching an actual mission. So you have Lander, you have Voyager, you have Viking 1, you have all of that. Now, the probe that was launched on an alien soil was our effort to go to Jupiter in the 90s. And Galileo was one of the missions that was launched to go all the way. So if you can imagine sending a garbage can, sending one of your wheelie bins, something about the approximate size of your wheelie bin, putting it on some wheels, truck wheels, sending it out into deep space so it can float around in space and take some pictures and send it back. That was pretty much the limit of our endeavor as a species in the 90s. But then, in 2014, we did something a bit more sensible. Rosetta, that was launched. I remember Rosetta, that mission, because, well, this was more of a recent, very recent endeavor, because last year, when Rosetta finally made touchdown at the, what was it, that little rock that it landed on, when I was actually at the UCL Observatory, myself and a couple of other friends of mine, we were taking pictures and then we were asked to stop everything. I was at that particular moment in time, right in the middle of taking some pictures using the Celestron C14 to look at some objects in the sky, and we were told, all guys, we have an important announcement, can you please stop what you're doing? And so we came in, what's going on? Rosetta has just made touchdown, it's landed. Now we need all of you to come up with objects and something, what do you want to study? So I was one of the first people in the country to actually say, okay, this is what we need, to make a suggestion. My suggestion, okay, me and a couple of us, let's do a little radar tomography of the soil, see what sort of terrain we're in. The next day after that, power shuts out, because again, this was a solar-powered device, runs on solar energy, and where it landed was awkward. It was not facing the sun. So, can you imagine? We deal with such ridiculous problems. A lot of rocket science is dealing with petty, ridiculous nonsense, which can really dampen an entire civilization's quest to do something more meaningful. So, 2020 is when we actually feel first humans might be on Mars in the 20s. We hope, but you know, that's again.
First you will be okay.
So far, we have what we call robotic exploration, which is NASA Surveyor in 1967. The beginning. So a lot of space exploration is actually robotics, ladies and gentlemen. It's all about applied robotics. In my undergrad astronomy course, one of my close friends, colleagues, she works, she's an IT programmer, but she does a lot of, what do you call it, work with robotics. And her professor, when she was doing her master's, was one of the people that worked on the Mars device, the robotic arm, to write the code in order for the computer to message the machine, to move its arm and do things. So a lot of that was robotics, and a lot of space exploration was not really that useful, pretty much because technology and the engineering of our planet is not really keeping up to the science. See, the physics, at the moment, space science has come down to 3 important fields. One is robotics. Second is the engineering and materials. The third is computing, IT, mainly programming. Those are the 3 key pursuits that can either assist or to hold us back in rocket science. A lot of the actual astronomy, cosmology, astrophysics, that's not the problem. Our problem is actually dealing with simple issues. So, Viking 1 and 2, the Mars landers in '67, going back to what I was saying, exploration has been robotic, so a lot of lessons were learned when we look back at how we did things, building simple objects that can move in an alien environment, things that work on rocky, rugged terrain, just building machines that can go off and do stuff. This is as far as we've gotten to. Now, 2008, Felix Lander did something a bit more sensible. Felix Lander actually has what we call the excavator arm. Now, this was, again, it doesn't seem very significant, but it was a very big achievement. Pretty much because it made it possible for us to finally see what is possible, what we actually can do. So you've got something that actually has tools built into it. Now, the Rosetta project was slightly exciting purely because it had, harpoons, it had instruments, it had machines that can actually do stuff, pick up the soil, collect samples, look through things, X-ray. So this is the direction of where technology is heading in. Now, the Chinese in 2013 have gone one step further than NASA and we have, because Chang'e, the third, what we call the moon lander, or the rover, as we call it, called a rover, but in 2013 they launched this object where it can go down into the soil, look around and do more things. Because normally what we do is when you put a camera onto a device, all it does is it makes a little screenshot, makes a little shot of, it takes pictures of everything surrounding it. But to get something that actually can do more, artificial intelligence is quite useful here because you've got autonomous decision making. The sort of drone technology that we use can actually be useful here because you've got a machine that can think independently. It knows what to do. So this is the next level of where we can head to. There's another little device here which I haven't actually brought into my slides, but I can talk my way through it. It's called Hayabusa, the Japanese Falcon technology. So Hayabusa in Japanese means falcon. What it does is, it does what we call a dive bomb, sort of an expedition. It doesn't actually land, but it can go down, go very close to the terrain and then do what it needs to do, pick up and go. Interesting bit of technology. So that's a newer version of what they've done. However, our direction of where we're progressing, after getting devices that can move and get stuck, getting devices that can move and dig themselves out of trouble, getting devices together that can move around and actually do more stuff, we're now coming to a stage where a lot of robotic effort, after a lot of experience with robotic effort, we've come to a realization that direct human intervention is essential to exploration, to both evidence gathering, data collection and analysis, and also surveying alien environments. It is necessary for a human expedition, and it's just about time as well. So here comes the challenge. We need people in space. We need to send people out there. We've put people on the moon, might get people onto Mars, don't know. So now we're looking at what are the key challenges to getting people out there. So, first thing I will do is to define the term. Exploration is essentially the sustained long-term exposure to a non-terrestrial environment. That's our definition. The other element of exploration, the next level beyond that, is permanent habitation in a hospitable planetary terrain. So when you actually spend a lot of time in space and you actually build a base in deep space. So what we're doing now is developing a mature atmosphere conducive to and supportive of hominid life forms. So the third bit is not actually exploration. The third bit is terraforming, which means when you go out there into an extraplanetary body, an extraterrestrial object into space, whether it's a rock or whether it's something the size of the moon, whether it's Jupiter or whether it's an exoplanet, something which is an Earth-like planet. For you to live there in a sustained environment, firstly, it must be an environment that can sustain you. So when we go in and you build a complex, which is where we are now, you're looking at a major initiative, a great venture. You must be willing to send people out there to build a complex and then to stay. So you need an Earth-like planet with what we call a secondary atmosphere. So this brings me to the actual point. Habitation versus exploration. Two types. Type 1 is exploring a habitable zone. What does a habitable zone mean? Something close to the Earth, which means a mature atmosphere. And what is a mature atmosphere? Something that has both a primary and a secondary atmosphere. A primary atmosphere could be something like the Moon. A secondary atmosphere means it's taken millions of years to form. It has the main ingredients. It has oxygen, it has carbon, nitrogen. Again, most of the planets out there are hydrogen abundant. You have gas giants, ice giants, so they have atmospheres that are rich in hydrogen. However, you need a planet which has just the right oxygen content to sustain a human life form. That's the important thing. Secondly, atmospheric pressure. You need one that has the greenhouse effect, that can basically sustain, well, intelligent life. These are the conditions of what we call exoplanet, Earth-like planets. Again, the other problem is we inhabit a place that we call the Goldilocks zone. How far? So normally people that do exoplanets, extrasolar planets, when there are scientists I know that spend a lot of their time looking for Earth-like planets, habitable planets. So the most important thing is it's the distance that the planet has to its central star, which affects the possibility and the probability of life. So how far or how close you are to your star. What kind of star do you have? Is it mature? Is it a G-type star, O-type star, B-type? How big is it? How hot is your star? Many Earth-like planets have what you call a binary or a trinary, dual star system. They have 2 or triple stars. So when you have a planet, how many stars does it have? Secondly, its distance from its star. Third, the size and density and mass of the planet. Most of the Earth-like planets are the size of Jupiter. So you know that, again, these are all very significant when you're exploring. Because again, the size of the planet affects gravity. It also affects, its force. When you're building machines, you have to bear these things in mind. Also, if you're on a planet that's much bigger, you will weigh a lot more. So if you want to lose weight, go to a place like the Moon that has low gravity, your weight will be far. So it's an old joke, I mean, it's a terrible one, but you might as well laugh because this is as funny as it's going to get.
I should say, it doesn't necessarily have to, you don't necessarily have to weigh more. How planet's mission of gravity?
Of course.
It's spinning your way, that's...
Yes, it's true. So the other thing is, how many moons does it have, which affects spin, and things like that. All of those things will affect the temperature of the planet, how hot or how cold it is. Which brings me to the next thing. When you're on a foreign body and you want to do what the Chinese are doing, which is to build a complex, build a dome. So right now on Mars, you can build what they're trying to do, one of the missions that Imperial College London is doing on behalf of the Chinese government, President Xi Jinping was very generous when he came over a couple of years ago, and he made a very generous £1 million donation to the Astro team. So a lot of people, PhD students mainly, are involved in developing these habitable zone complexes on the Moon and on Mars. Now the other thing is, you have to be very careful when you build a complex. The most important thing is what? What do you need when you go to another planet? What is the most important thing? Very first step, what do you need to build? Even before that, what do you need to do first?
Energy.
Energy.
Yeah, but even before that, what? You've got to find a place to land. Landing. That's the most important thing. Finding a place which is safe. Finding what we call a favorable surface area. That whatever technology you're using, it needs to be a place on which you can land. Secondly, that place on which you land must also be a place from which you can take off. Because think about this, in rocket technology, building a craft means it has to be able to land and then take off again. That's the most important thing. Without that first step, you don't get anywhere else. You're not going anywhere. You have to get there first, and you have to reach safely. Think about that. So a landing base, a landing pad is the first step. The next step is what? Mining. Space exploration means interstellar mining. What minerals would you get if you look at bodies, objects, asteroids, comets, bolides? Type 2 is what we call terraforming. NASA's Planetary Science Vision in 2050, they had this workshop. I mean, okay, it's not last week, because when I first did this, it was about a week. But the first was titled The Terraforming Timeline. So this paper presented an abstract for turning the red planet Mars into something green and habitable. The second was Mars terraforming the wrong way, which rejected the idea. So you had a discussion and a debate, where some people believe you can go out there and you can terraform, maybe turn the planet into a hospitable zone, doing one or two different things. You can read it, it's available. Challenge 1, so the first challenge is to do with habitability, like I said. Habitable zone, which means exoplanet detection. The closest exoplanet is close to a light year away. One that's closer to that is Polaris. I think. So there's one close by, but it'll take us more than a generation. So you have to bear in mind, going to a habitable exoplanet is not possible within a generation. Which brings in, again, scientific thinking. How do you overcome these challenges? First, you have to think of generational colonization, which means you have to get people who can deal with habiting deep space, and then 2 generations.
You can look at my paper and how to build an FTL warp drive spaceship.
Ah, yes.
We'll get there a little quicker.
Okay, yeah.
It may take half a generation to build one from now. But
Of course, warp drive is another thing. I mean, there are several brilliant ideas. Warp drive is one. The other is what we call microwave propulsion. There are various ideas. I mean, there are certain workable solutions. I will go into that towards the end. But yes, one of the most important things, if you're inhabiting an exoplanet, it might take a while to get there. The other is multiple stellar systems that you have to think about. How do you do? I mean, this is good. You can build solar-powered machines if you're in a system that has dual stars. So you can feed off one star and propel yourself through it, and then go to another place, use the other star. There are ideas on that. Third is chemical compatibility. You need to have a planet that is chemically compatible with the human body and human mind. Third is greenhouse, like I said, low or high pressure. If the pressure is too low or high, like Venus, I asked my professor when I was a student, he used to say, Venus is hell because she's a woman.
Okay, well, moving quickly on.
So, mineral abundance, mineral rich in the sorts of metals. Now, if you're inhabiting a place in the galaxy that's got mature, well, the metal composition will say but a galaxy is quite old, because again, they say a lot of planets that are formed from the metals that were inherited from the death of earlier galaxies. So that's one idea. Now, the most important thing, the biggest challenge to getting out there in space is, it's high risk. Think about it. You're basically on a rocket out there. It's very risky. It's really unsafe. It's high risk and it's very expensive getting out there. Now, another old professor of mine, Matt, who works at MSSL, he said this to us that, I was in the lab, most recent was last year, looking through the rockets that McLaren and some of the other companies that sponsored the instruments and what you're doing. The most inefficient, we currently use the worst possible way to get out there. Even Tesla's Dragon, this new launch that worked, it's terrible. Because what you're doing is you're putting a bomb. You're putting billions of dollars worth of equipment on a bomb. And you're basically hoping that the rocket propels. Anything can happen. Do you know how many failed launches you have to go through? 100. Elon Musk, how many, was it, 100, 200 million that he burnt up and wasted, flushed down a toilet every time the thing collapses? It's a high risk, highly expensive maneuver. It's a financial nightmare.
And the cost on there for the lives of people who lose their lives.
Yeah. You're asking people to risk their lives. You're asking the smartest people on our planet to put their lives on the line. There's something that may not even work. Second problem is constrained living environment. You see, the key to getting efficient rockets are all about weight management and space management. We're trying to make things as light as possible. Reduce the weight that it needs to carry. Increase the payload, increase the fuel, and reduce the weight. This is always the issue. It's always the problem, the challenge, the cost-benefit analysis. And you're putting things, you're trying to miniaturize everything, make it as small and as lightweight as possible. And you're asking people to fit into something, huddled in. So the living environment. So if you imagine, you've got right now single person or dual manned space shuttles are. You can only fit in a small team. 2, 3, 4. The last ISS mission you have what? 4 people? So they're like the 4 superstars, superheroes. You get 4 people into a tight living environment. The second challenge is energy, which is to do with material sufficiency. Now, here's the most important thing. This is why you have to always plan these things the economic way, economic feasibility analysis. You're always planning, like game theory, one step ahead. Because when you send something out there, you need to have a self-sufficient mission. What does that mean? Self-sufficient mission is a mission that can actually find its own fuel, that can extract its survey its environment to extract the fuel needed. Self-propelled. So if you're out there on the planet, you need to find a source of fuel. So mineral composition is important. What sort of minerals do you have on those planetary bodies? Third, can you use any of them for fuel or raw material? Because right now, thorium, nuclear technology is as necessary, because you can't just rely on solar power. Because out there, on a body that has no wind, you can only use solar energy, or you can use other forms of fuel, supply of nuclear energy, which again has its own problems. Third thing, now we have this device, which is what we call the 500-day configuration of a mission, where you can plan to have something that can sustain itself for 500 days. That's about as good as it managed to get it so far, one of the longest missions that are out there. So, that's a schematic of a very simple way how they send a complex out there. The third issue is technology, like I said, landing and takeoff, key issue. You need to build a platform when you get somewhere. Third is high risk debris impact. You could get, when you're out there in space, you could collide, you could get hit by stuff, you never know. If you get hit by something the size of a golf ball, that's it. game over. So those are all sorts of risks to consider. And the other issue is mainly micrometeorite impacts. Micrometeorites. Because when you go through a debris field, even dust particles this small can cause a great deal of aggro, depending on the type of equipment, technology and mission you've got. The other thing is, with people out there, solar exposure can be quite high, it can be quite lethal as well. And the problem of having nuclear power in space is when you jettison a device, space debris, you're polluting, destroying, contaminating an exo-environment. We don't even know what risks can be to other, if there is other life, we would have ruined it. So, if you think about it, if you're getting people manned mission, you have to have people who are willing to bear the risk of cancer, solar exposure, risks of all sorts of things. Most important problem of our time is human DNA. How do you get people to sustain themselves? Because again, in low pressure, deep space environments, DNA mutation happens. Telomeres lengthen, which means that sometimes it can extend or reduce your life. It can also affect you in a number of ways. So human DNA tends to break down and degenerate after sustained exposure to certain harmful forms of radiation, other bacteria, we don't know. So DNA risk, especially with the heavy ion track impact, and you've got cosmic rays, gamma rays, you've got all of these things that are constantly interacting with the human biology. The other problem is the risk of sending people out there is the breakdown that happens to people.
I was just going to ask you about that, the psychological breakdown, because there was and that's starting to, how do you deal with that, like people psychologically?
Exactly. Now, astronauts that went out there into space, and they came out, and some of them lost their mind, committed suicide, went drugs at risk, and people go mad. People lose their minds because you're asking people to go out there, and again, in what we call zero gravity, low gravity or zero gravity pressure environments, human neural anatomy also changes. People's thinking, and you're asking people to be lonely in the middle of a dark, deep space. It's horrible for people. Psychologically, the body decays. You have bone degeneration, breakdown when you're not in a gravitational field. The other thing is long-haul trips do affect people's minds. If people are not, that's why most of the people are who go on to these, some military Air Force pilots, are people who are highly, lone individuals who can operate under certain conditions. They get psychologically tested, yet still it doesn't work out well for people in the end.
Can I just say that I think this is a non-problem, and I'll tell you why. I think it's the opposite thing as a problem. First of all, it's easy in technology to give people a geo-acceleration, just spin the ship.
Yeah.
Secondly, if you want to go to an exoplanet and you want to accelerate a human, you have to accelerate it really quickly. 4Gs.
4G.
Now 4Gs is not 0G.
No.
4Gs is a pain in the backside. And it's a long-term one. So the problem is the opposite. 4Gs, you can just about live and get somewhere.
Sure.
You accelerate all the way halfway there and decelerate half the way back. You can go nearly anywhere if you do the maths in the universe like that, because it goes so fast that you're almost relative.
4Gs, definitely. However, Air Force pilots who've gone in either Mach 2 supersonic flights, and a lot of the people who are pilots and captains of these ventures, 3, 4G, for them as well, it's again, the body sustains it's physical damage.
But it's the opposite of this problem.
Sure. I mean, so if you are in a low gravity environment, the mind gets affected. So it's either the mind versus the body. So again, something is going to take a batter, regardless of how you look at it. The other thing is bone marrow degeneration and the risk of disease and contamination in space. Like I said, talked about radiation, but again, right now we're thinking about ways of how to get people out there. Now the most important challenge now is what I call ethical exploration rather than colonization. We have something in America called the Commercialization of Space Act, which gives corporations, Google, various other aerospace firms, private enterprise, private businesses, what I call the corporate right of claim, the right of first claim, which is specified when Obama passed this into legislation, the bill got passed. they're allowed to go out there and to claim any object as their right of first claim. Now, if you go back in history, if you go back to human history, you don't need to go far. You don't need to look far. Look at what has happened on this planet.
Yeah.
When one race, when one nation, when one individual corporate entity occupies a space-time that is other than their own, how have they behaved? How do they conduct itself? Look at colonization, look at the costs and the consequences on our very own planet. So before you even talk of colonizing and exploring something out there, how have we behaved towards ourselves and each other here? That is the more significant question, in my opinion. That's the most important issue here.
Yeah.
What we're doing, how we conduct ourselves here and how we conduct ourselves out there. Discarding, jettisoning cargo. For example, when you take fuel, injection cell, and you're out there and what happens is you dump some of your weight in order to then thrust further. What happens to those capsules and cylinders? We're polluting and contaminating out there in space. So this is a massive problem for sustainability. Now, my initial PhD research topic was about the ethical exploration, building an ethical framework, sustainable standard for aerospace exploration organizations. And I had a great challenge getting a supervisor. I had a terrible time finding professors at Cambridge and anybody who was interested, purely because the companies and the entities that sponsor research are essentially at odds with a lot of the ideas that I'm sharing. Morality, ladies and gentlemen, gets in the way of corporate bottom lines, as we all know.
Exactly.
What about other life forms that we're polluting, we're destroying?
Don't have to look far.
Don't have to look far. What about other life? Imagine if we abandon one of our energy cells or our equipment somewhere, we dump it. What are we doing? If there is any life out there, we would have ruined it because we've already contaminated the surface of Mars. There's heavy already in the 60s, in the 80s. Who is going to bear the responsibility? See, so we need a responsible human governance of aerospace. With the Commercialization of Space Act, the way is open for exploitation, for corporate malpractice. Since this is a new area, as yet unexplored, no legal, business or CSR frameworks put in place. That was from research, my PhD dissertation. But anyway, that's just an idea put out there. Now, commercialization of space. There's something called the Space Foundation that wrote this report in 2015 that estimated the global space economy. We have now commodified, corrupted and prostituted anything to do with exploring space, just like we do everything else.
Yeah.
So the space economy is worth 330 billion. That's what the accountants estimated. The potential return on our capital employed should be up to 300 billion. So if we exploit and manipulate, not just our planet, but the whole universe. That's what we stand, that's the profit we can make. Isn't that brilliant for Google? Isn't that great for our shareholders?
It's interesting those numbers when you go for P and then lose. We learned that 2.5 billion people on the planet don't have toilets.
Yeah, we're talking about
Thank you.
space.
Thank you. Thank you very much.
Every single animal pretty much doesn't have one.
They do if you're back down.
So 9% increase over last year. So the annual report from the Space Foundation tracks government spending. Now that's a small, if I say to you, that 300 billion figure of space economy comes mainly from commercial infrastructure and support industries, commercial space products and services like ISS, servicing space stations, mainly technical maintenance staff and just sending goods and services to sustain people who occupy, who on these space missions, and government space budget and non-government, which is another nice way of saying, non-US government budget is a very nice way of saying, quote-unquote bracket, the military-industrial complex.
Yeah.
All of this, the biggest investors in this are military, unfortunately. So what next? I mean, beyond the local group, we have all of this. I'm just going to go through a few solutions to these challenges very quickly. Solutions. So the projects we have so far is what I call pod technology. So don't bother with the text, but inside the inner solar system where we Earthlings reside, sunlight is the natural choice, so we can use solar-based technology. The other is, again, nuclear power. The third, of course, is what I call the ability of wave propulsion. There are other forms of propulsion, other forms of fuel that we can use, which is available. And the other very important thing to sustain life out there is food, which means growing crops in space. The idea of extrasolar greenhouse, which is what a Japanese professor has been working on. And quite recently, in 2013, microgravitational horticulture. It's another new word for parties. Plant roots normally grow downwards. However, in space, roots will grow in every direction that they can, and water and other ingredients will normally float up. So what they did was get these little pressure chambers where they successfully managed to grow some crops. So you had, what was it, lettuce? So they've got this thing, the veggie in the International Space Station, that's a container that gives the plant more guidance using natural pillows, using what we call plant pillows. So bags of dirt, fertilizer and nutrients equipped with materials that can absorb nutrients from the water. So astronauts normally will glue the seeds.
Does anyone know, I don't get why they didn't build the International Space Station on 2 sticks and just let it rotate? Was that better than everything?
What, like in 2001?
Yeah, what the hell's the problem?
If you look out of the window, you can't look outside.
Oh,
there's nothing spinning.
Oh, that's what it is. Okay.
Yes.
It's really service oriented. You don't have to put artificial windows in, and the human needs depth. They need to look far.
Can't you put the humans in the one rotating, but if they wanted to?
Or holographic projection, that's the other thing, holographic technology. Give them some graphic visual scenery. That's what normally tends to work with astronauts.
Well, it's what works underground as well. They put false scenery.
Oh yes, very good.
Underground monetary bunkers.
Yeah. So the other idea for space, getting things out there, is gravitational assist and Lagrange point docking. So NASA used these, I mean, you're probably already familiar with the Lagrange points, how they dock in the Earth-Jupiter system. And so you've got several systems where you've got the docking that happens. For example, you've got the Sun and the Earth here, the asteroids. So you've got L4 and L5. So the Lagrange points are where you can successfully dock ships, because those are areas which NASA tends to use more frequently. So gravitational assist is useful because this is how they've used Jupiter, previous missions, to successfully use the planet's natural net force, the pull, to thrust and propel your craft onwards. So you save a lot of energy by using its gravitational
You
propulsion.
showed the error the wrong way, I think.
Yes.
The Jupiter error should be direction motion.
No, of course you're right, but I think I didn't have much time. I just took the lift of that picture somewhere. Now Rosetta's 10-year journey, if I was to just use that as an example, they used the assistance of gravitational, assistance that they used on the Mars mission in 2007. How they kind of rendezvous, they got these points taken from the French ESA's website. So I'm just going to finish up soon. So that's where we are. This is what we're going to in the future, putting a complex together. If you imagine Mars as it is now, once they have landers, once they build the complex, the Chinese are going to be on the first. You also have NASA that wants to do something very interesting. They want to take an asteroid. There are a couple of aerospace companies and big firms that have already laid claim. So they're going to spend maybe, if it goes ahead, spend $1 billion, get this thing, an artificial object, that's rotating and use that as a station. So you've got countries that want to, and companies and countries and entities that want to colonize, claim and own, lay their ownership stake to various bodies out there. I personally believe this is a disaster waiting to happen. I'm strongly an opponent of this way of doing things. I basically believe if you're going to explore, you need to do things in a certain way. The right way. There's some future space missions, and in case we are lucky, one day, if we're fortunate enough to meet other life forms,
Grandma!
if we ever get there. However, before I close, I'd like to say one thing. We've talked a lot about space. Now, I know somebody, one of my colleagues in my earlier project that we've worked with, Kirk Sorensen, he was doing the same thing, building a complex on the moon, using a form of thorium reactors to propel, to create the energy needs. And then he decided, why should I spend all this effort to go and do something on the moon where I cannot even solve the problem of my own home planet? I'll ask the same question again. What is the point of us going anywhere out in space? If we can't solve our own problems, we're going to end up being nothing more than cosmic parasites, vampires, sucking the life out of our own world, destroying it. We're going to go out there and do the same nonsense. If there was someone with a bit of common sense, I don't believe they would allow this to happen. Before we think of going out there, we need to first clean up our own mess, because listen, no other species that we've encountered here can be this hostile and aggressive and malevolent towards its own kind. No other being out there, I don't think, would allow half of its own world to suffer this way. No other being would justify the sort of costs that we are willing to go through, the things that we sacrifice in order to pursue something so meaningless.
Just what I hope that somebody doesn't go all with the planet, realise it's infested with humans looking things up.
I'm cynical enough to believe that they all would be the same as us.
They would be just
like us.
Yeah.
But I'm cynical enough to believe that.
No, but here's the whole point.
Why are we looking without instead of looking?
Why aren't we looking within ourselves? Why should we look outside? Because man has always looked up to see something, look for hope. He looks outside instead of giving hope to his own. So before we go out there, we need to first look at ourselves, clean up our own mess, and then go out there. And if we go out there, we have to do things properly. Now, this is my belief. These are my ethical principles and my values and what I stand for and believe in. I'm just stating what I believe to be true. What si Caesar privatus portuse set, magis oratio non mihi opus est. If Caesar hadn't died a private death, there would be no need for me to be out here making a funeral speech. As Mark Antony once said, I come not to praise Caesar, but to bury him. The way we do things is entirely wrong. Before we get out into space, let's clean up our own space. Let's become people of integrity first. Nations, all humanity needs to go out there under the right circumstances and do things the right way. It cannot be secret government negotiations, military institutions, and private companies sending soldiers out into space. Colonization or exploration is a human effort. It needs to be done by real human beings. I will close there, ladies and gentlemen. Thank you.
A comment and then a question. I believe in an entropic multiverse, and I think by design stars are multiple light years away, so Nazi marauders can't go there so easily.
No.
My question is, many that I talk to think to terraform Mars would take a couple of thousand years, something like that. I want to see if you agree with this. It was about 30 years ago I read a wonderful document that said it could be done in 300 years. You put some 10-kilometer mirrors up to focus sunlight. You start with microbes, then fungi, and then before long you've got an atmosphere, maybe initially enough to grow crops or something like that. Do you kind of think that with the right system you can do it in 200 or 300 years?
it is something that we need to explore. See, I personally believe it might be possible. The conditions for life have to be right. But again, going back to my definition of life, what is life? See, the principle of what we would define, you can get organic process. I mean, we're looking mainly, we're talking only about organic life forms based on our own narrow bandwidth of definition. In a holographic multiverse, in a higher dimensional verse, you wouldn't know what sort of life forms would exist unless you've encountered some. The basis of life that we have are based on our encounters. So we think all life would be organic. If life would not be organic, what if life can be photonic or phonomic? You have light beings or sound-based beings. You have beings that are species of pure thought. We wouldn't know, would we? But here's the point. This is what I'm saying. Yes, conditions of life can be possible. However, we have to, again, broaden our definitional focus, what we would accept as life.
Sorry, John first, then Anton.
Yes.
Okay, I like, just to comment on what you just said, I mean, I like the photonic or photonic idea of life, but what makes you think it's not like that already?
I'm just saying, you know, like I said, it may very well be. It probably is.
Okay, but what my question was about was something different. I think you missed out some of the, not for planetary or solar system explanation, but for extrasolar system. I think you missed out the most important things in your talk. So I'll just briefly say what I think now. I think the main problem is you have this idea of carrying fuel and perhaps starting fuel cells and stuff, and off you go off to a planet, Sirius, or off to a star, Sirius or something. But if you do the sums, you'll find that even if you could store energy, it's pure energy.
Yes.
You can't carry enough with you to do what you want to do.
No.
It's just not possible. So if you really want to do stuff like that and you want to have your 4G acceleration, you need to find some way of some other than nuclear, thermonuclear, or even antimatter storage, which would be the best you could do, means of generating energy along the way, or picking up energy along the way. So I think do the maths of that. The first thing is not to land; it's to get there.
Yeah.
And for that, you need an energy source. So energy was the right answer, I think, to that first question. So that was going to be
energy.
Most of
that problem has actually been solved. There are people there are people that I know, but they're not well known. They're not out there. But they've got. I mean, I am aware that they do have solutions. It's just it's not public.
Who are they? I want to talk to them.
Of course you would. I'm sure you would. And then, you see,
and they want to talk to me.
Okay. Anton?
So I thank you very much for the enlightening talk. The one question I would like to ask is, so we're looking for a planet in the so-called Goldilocks zone. Goldilocks zone is basically defined with suitability and suitable far enough away from temperature.
Sure.
Yesterday we had a trip to Avebury and Stonehenge, and one of the sort of experiments we did there was sort of divining. We walked around, some of us divining once, and some of us said, you know, there is something unexplainable. Now my question is the definition of the Goldilocks zone complete? Because if it's not complete, if there are other energies that are required for the life energy which the Mother Earth is giving us, as soon as you go out there, this might be missing, and the whole life reproduction and sustainability will no longer be given.
Just wait till the sun creatures notice this one.
So what's your opinion on that?
my personal view, my own personal view, my opinion, what I believe and know to be true, Goldilocks zone is a rather subjective definition. Now, life can and will exist anywhere that it needs to exist. Life will always choose life and find a way. I know that, I believe that. Secondly, we're talking about life from I'm talking about biological, organic is one thing, but consciousness itself, that's a whole new can of worms, a whole new ball game. Anybody who has encountered different forms of consciousness will probably attest to this fact that, listen, what we think we know is very limited, very little. There is a whole lot out there a whole lot more out there than is publicly known, and people be willing to acknowledge and admit to. And there are people, life on this earth exists, adapted and habituated to this earth. You know, people, here's the thing, you may not necessarily, I mean, you're talking about something that as a being, but going even further, as a soul, what are you? Who are you? Where are you? See, those are things that are, you know, so you've got the people who divine words, you've got people who tell you that the earth has certain energies, and we are suited to those types of energies. You don't know that when you see, Native Americans have said this before, indigenous cultures have had this belief that the earth is a living consciousness, it's a living being itself. And everything that is out there, the sun probably has its own consciousness, it is a being. Everything out there is a being. Now, I know a Russian professor who has actually proved it scientifically. He's actually proven that, okay, energy and consciousness will affect even matter at the material level. And you don't know the sorts of beings that actually do inhabit this greater realm. Not just in their energy, in their intellect, in their consciousness, but in their capacity to influence and affect outcomes and change. You're dealing with forces that are beyond your comprehension. That's why I mean, what we do, going into space, it needs to be done with the right energy, with the right consciousness, for the right principle and process. That's my point.
Yeah, we'll see.
May the force be with you.
What do you think it will take to shift the political conversation on this planet to bring us to the point where we could really do this?
It's the idea, basically, that historically, the Earth has been far more civilized than our current understanding of this history. We are capable of so much more than what we're actually manifesting right now. Now, there's this idea that you only create things that you use. You will only ever create things that you need. Now, the consciousness that creates things, you have to go back and analyze what are its interests and its needs. You see, I think to shift the political conversation, you need people to become more conscious first. Again, you have people, you have political structures on this earth. If you look back, I actually feel that there is this karmic, residue, this trace, that for you to create changes on the planet, you have to address the cause and effect of it. Now, the cause of it, the causation of everything, politics, anything that's to do with powers, power on this planet, whether it's corporate, whether it's investment or finance, influential, so people with power. Any position of power always attracts power seekers. It's the type of, behavior and consciousness that's attracted to positions where they can influence. And and this is again an energy without empathy. The people who are politicians, people who are in charge of this, are essentially the most psychopathic individuals.
Yes.
Yes. Purely because, again, if you go back, there's this idea in, this Taoist, the Zen Buddhists who have this feeling that this mandala, it tells you about life on the earth in a very simple pictographic definition. The 6 realms of hell before you get to heaven. And in that you see one is the realm of warmongers, power seekers, jealous gods, hungry spirits. So all of that is defining essentially the archetypal human behavior, the energy. People who are attracted to positions of power and influence tend to be of a certain type who are willing to do any, get there by whatever means. They're not the people who share or represent the consciousness of, the planet. They don't speak for the world. And they don't represent what is best in people. They don't necessarily represent the people. That's an institution that will fight for its self-perpetuation. So to shift the conversation, you have to wait. Right now, what's happening on the earth is really interesting. The world is changing to a state where the young people that are being born on the planet, the type of people who are coming up through the ranks, are essentially people who will no longer stand for this. So these institutions and structures need to collapse. Collapse is inevitable, just like the financial world, Brexit. This collapse is necessary for something better and new to come. So you highly have an emergence of people who are more aware and conscious, then you have the right political leadership to change.
Only a very quick comment, that's it. And then we need a coffee
Very
break.
comment. I think you're absolutely right, but I think we need to put ourselves in a position where we force the position where the scum that has risen to the surface is no longer has the power to make the decisions on the planet, and the whole feeling of the majority of people on the planet, which is a natural and proper human feeling, is that thing which is in charge. Like the situation that happened in America when the civilization so-called became into a state of much better state of harmony
And just
with nature.
simple acknowledgement of what's gone on in the past. The only way you can move forward is to acknowledge what happened in the past and realize that your actions affect everybody. So I just think that it's just simple acknowledgement of what rights or wrongdoers been grieved or whatever, just acknowledgement of it. Just be aware of it, that it exists, and just.
I think it should be included something AGM to fix it.
Thank you.
Withdraw for a coffee.
Yeah.